So I'll be presenting VeriZexe, and my name is Alex, and this is joint work with Binyi and Zhenfei and other colleagues at Espresso Systems. So let's start by looking at how computation on most of the blockchains work today. Roughly, we have, at the beginning of a new block, from the perspective of a smart contracts on these systems, you would have a program lives under a certain address, and you have the program logic and the program states. Now, there's incoming transactions that specify how you want the state transitions. And when processed, these transactions is going to update the program states. And as we can see in this model, the program states, input data, and the caller who's initiating these transactions, all of these fields are public, and they're permanently stored on-chain. And this is sort of important for public blockchain to achieve public verifiability, which means that any nodes in the systems is able to re-execute these transactions and agree on the state of the systems. And Zexe is this work that is shorthand for zero-knowledge execution, is a work that's been proposed in 2019 to address the privacy issue of most of the paradigm that we mentioned. And it has the following properties. First, it provides a privacy. It provides data privacy, which means that the program state before and after the updates are hidden from the public. And it also provides a stronger guarantees called function privacy, which means that transactions which are updating the states does not reveal which programs or which function exactly are you interacting with. And just quickly, intuition why this matters in some application. Imagine you have a smart contracts that are bookkeeping or keeping track of the token balances for USD token. And data privacy basically says that the mapping between who has how much is hidden from the public. And the function privacy basically says even if you can scan all the historical transactions, you're not be able to tell who has interacted with this contract at all. So you won't be able to tell who is the who has potentially have some assets under this address. On top of privacies, Zexe also provides, maintains a public verifiability and succinctness, where verifying the transaction is very fast, and the transaction size itself is very short, usually under kilobytes. Apart from the security properties, it also have rich programmabilities, where the users is able to define arbitrary data. You can write your own programs, and these programs can interact, just as you would expect from any general smart contract platforms. So in order to build up towards our problem statements, let's understand a little bit better on how Zexe works. At its core, Zexe is an instantiation of a scheme called Decentralized Private Computation, or DPC for short. So DPC is a scheme that generalized an earlier work called Zero Cash, in the sense that if you think of Zero Cash as a single private payment application, then DPC is a private smart contract systems, where you can support multiple applications instead of just a single one. And the core idea, also the data structure, they inherited from the Zero Cash and use a UTXO transactional model instead of the account-based in Ethereum. So the core idea is that instead of putting everything on-chain and re-execute on-chain, what we do is we take the execution off-chain, and what's being posted on-chain are just simple state commitments. And we're using hiding commitments so that these they do not reveal anything about the state itself. And to guarantee that the correctness of the off-chain computation, whenever we're doing a state updates or updates of the state commitments on-chain, we have to attach a cryptographic proof that are succinct, which are fast to verify and very short, and also zero knowledge. And the privacy of the system really comes from two parts. One is the hiding property of the commitment schemes, and the zero knowledge property for the proofs. And of course, as the previous talks already hinted, we're using Zexe snarks for the proofs. So in the schemes, we have a prover and verifier, and the prover is trying to convince the verifier that given some public instance, I have some secret witness that will satisfy the circuits, which specify the relation. And in our settings, we're interested in pre-processing snarks, where before the proving stage, there will be an offline pre-processing stage that will generate a reference stream we call a structural reference stream that contains the proving key for the prover and the verification key for the verifier. And then the prover is going to generate the proof and send it to the verifier, who will either accept and reject. Thanks to the previous speakers, I won't go into the details of all the properties here. The things that we want to focus here is the structural reference streams. Now, different choices of snarks requires different types of SRS. And roughly, there are three types. One is the circuit-specific types, circuit-specific snarks that require trusted setup per circuit and per applications. During the setups, you have to you will generate a trapdoor that you have to throw away. Otherwise, you will break the soundness of the proving system. So in practice, you need to conduct like an elaborate MPC protocol to do the setups. A relaxation or improvement on that is a universal setup where you only have to do it, one single universal setup for all the circuits or subsequent application of some bounded size. The third one is transparent, which is the best. You don't have any trusted setup, but usually snarks, transparent snarks suffers from larger proof size. More concretely, usually for reasonable security level, they're like more than 1 megabytes. And usually they are non-constant size. And for blockchain application where on-chain storage and computations are heavily replicated, so we want like constant size verification and constant size proof, regardless of how big the off-chain execution is, right? So we'll be considering the first option in this talk. So now we know that we can use the magic, we can wave the magic wand and generate using Snark to generate the proof. And these are the 4 substatements that this proof is attesting to. And for our talk, we only need to focus on the last one, which you can see there's a bunch of predicates that needs to be satisfied, right? And these predicates, you can think of them as defining the program logic. So they are defining what constitutes a valid state transition for this particular program. So, so this is program-specific logic. Now, if we were just to publish a monolithic snarks at the top, that's going to accommodate these dynamic user-defined arbitrary predicates, then we need to use something like a universal circuits, and which is known to be very expensive to prove. So original Zexe paper proposed to use recursive snarks as optimization. So the idea is that for this substatement number 4 alone, I'm going to produce a snark for it, and then what's being actually posted on-chain is going to be a proof of proofs. So this is called a proof recursion. What that means is that, first of all, I will need to generate inner proofs that are testing to the satisfiability of these program-specific predicates. And then I'm going to generate an outer proof that's going to attesting to the validity of these inner proofs. So more concretely, these outer circuit is basically have to run or embed the snark verifier algorithm. And of course, if we have a very complex verifier algorithm, that leads to a much larger outer circuit size that leads to a slower proof generation. And as a matter of fact, these outer proof generation dominates the cost of transaction, DPC transaction generation. And of course, because we're only doing proof of proofs, it's sometimes referred to as a depth 2 proof recursion. So here comes the problem statements. In the original Zexe systems, so they instantiated with the circuit-specific snarks. So the verifier, which benefits from a very simple verifier, so reasonably fast outer proof generation. However, the requirements on per application setup of the SRS is kind of unrealistic. Imagining like a developer came along to your private smart contract platform and he wrote a program, and he has to, for every program, he has to go outside and do an MPC. That is very unscalable. On the flip side, if you switch to a universal snark, then you have to deal with the much more complex verifier circuits. So in this work, we're trying to introduce some optimization techniques to bring down that complexities. And the conundrum that I was just mentioning can also be reflected by the benchmark. As you can see, in the original Zexe, it instantiated using Gross16 and GM17, both of which are non-universal setup, but the transaction generation is reasonably fast. However, the same author later on instantiated DPC using universal snark, using Marlin, and you can see the performances took a hit. Right? There's a significant deterioration on it because of the more complex verifier circuits. And our work, VeriZexe, is sort of trying to get the best of both worlds. So to reiterate, we're trying to instantiate DPC with universal snarks, but without much performance loss. And because of the universal setup, we don't have to do per app trusted setup. Now, more concretely, we achieve a 9 times faster transaction generation compared to other universal DPC, and significant improvements on memory usage. So now, for the first time, you can generate these proofs on your mobile devices. And at the same time, we retain the nice properties of Zexe. So for the remaining of the talks, I'll be talking about how we tackle the challenge of optimizing these universal snarks verifier circuits. The key takeaways are I'm going to highlight 3 expensive operations or sub-procedures that are very common, that we can see very common in the verifier algorithms in a lot of the universal snarks. And these are pairings, MSM, and modular arithmetics. And we're going to talk about our optimizations used in this work. The first is pairing. So a general recipe to construct universal snark is combining an infer-theoretical polynomial ILP with polynomial commitment schemes. The details doesn't really matter. All it matters is that the pairings comes from a popular choice of PCS, which is KZG. And the lessons is that if we were to constrain this pairing operations directly inside the circuit, it's going to take, it's notoriously slow and expensive. So as you can see, you will take like millions of constraint, but this is an R1 CS constraint. Might differs a little bit if you use different constraint systems, but very, very slow. So our idea is just to borrow the insight from Halo and later on accumulation scheme and now folding schemes to delay the expensive part, which is the pairing checks outside the circuit. So specifically, if you're doing naively and unroll the entire verifier algorithms inside the circuit, towards the end, you will have to do like a pairing, two pairings, and then do an equality check between them. So what we propose is instead of doing inside the circuit, we're going to push it outside the circuit and let the on-chain verifier do the pairings, which will be much faster, and we will end up with a much lighter weight outer circuit, so that the outer proof generation is going to be much faster. And note here that we have to publish the G1 group elements A and B so that the verifier can use them to check. But if we publish them directly, they will reveal something about the underlying secret witness, so we have to kind of randomize them. Another expensive operation is a variable-based MSM, and MSM has been covered by a previous speaker as well. So normally a common optimization or like algorithm we use is a specialized Pippinger algorithm, which they divide the B bits MSM into multiple instances of C bit MSM, where the C is smaller than B. And the idea is that with the help of some pre-computed tables of all the 2 to the power of C scalar multiplication results, you're able to do a space and speed trade-off, and the amortized cost is going to be lower, and you accelerate the overall computation of MSM. So a variable-based means that the table entries are not fixed. So each time with a different problem statements, you have to regenerate the table. Now, in order to incorporate this Pippinger algorithm inside the circuits, we deploy very common techniques called lookup arguments. So what lookup arguments are is instead of unrolling some expensive components like scalar multiplications inside the circuits, we're going to build a table that consists of valid input and output values. And during on-chain proving phase, I'm just going to prove that the values of the input and output wires are like forms a entry in the table. All right. The original Plum-Cup paper is targeting a pre-processed table where the table entries are fixed ahead of time. And in our paper, we observed and pointed out explicitly that the same techniques applies for so-called online or dynamic lookup tables, where the table entries are filled and decided during the online proving phase. And this is necessary for variable-based MSM. And just to show you the savings that we get, so the y-axis is the number of constraints that you'll get. So the purple bar demonstrates how much constraint required if you are doing the naive MSM inside the circuit. And the green bar represents how much you will require, the constraints required if you're deploying the online lookup table techniques. The last one I want to talk about is polynomial evaluation over non-native fields. So this also has been hinted by some previous speakers. The inner circuit and outer circuits are over different fields, and sometimes when you some of the verifier algorithms requires polynomial evaluations over fields that is non-native to the circuit, the field that the circuit is over. So you have to emulate the modular arithmetics. And I won't go into details of the circuit design itself, but I think the key takeaway is that while there are some general non-native field emulation, we exploit the extra constraint that we're only dealing with depth 2 recursion, not infinite depth or arbitrary depth recursion, so that we have some extra constraint. We know the relationship of the field size a little bit more, so that we can end up with a simpler design. So to sum up, we have proposed a couple of optimization techniques that kind of accumulate ends up with a pretty efficient turbo-Plonk verifier circuits, which only cost like 21K Plonkish constraints. Which I think is an order of magnitude better than the state of the art at the time of the writing. And that's all. All right, thanks.